Okay, what are we seeing then as we read this, read through this question? We've got the hydrated copper sulfate can crystallise with a number of different waters of crystallisation, compound A as the formula of that. We know straight away we're doing a water of crystallisation experiment. The student carries out an iodine thiosulfate titration, so we're going to do a difficult version of this to find the value of X and the formula of compound A. You need to get some highlighting through this section here. Yeah. So we've got two things. We've got the copper part of this and we've got the thiosulfate part of this. So starting with this is the copper part, this is A. Yeah, so we know we've got a weight of A. We know it's made up in that much there, but we also need to link this up to the idea that we only took 25 centimetre cubed portion out of it. Within the equation, that's where it's sitting. And then if we come all the way down to here, we've got the actual mass readings, which we can then do the subtraction of those two values there to get the mass of it when we come round to it. The other part of what we've got here is we have been given the amount of thiosulfate, or the concentration of the thiosulfate. That sits here amongst all of this. And the titration is about the volumes of the thiosulfate that we have there. So, other things that we might just remind ourselves of, that thiosulfate is connected to iodine in dividing by 2, and that the iodine is connected to the copper with a times 2. So when you do that to that. So just remembering that when we do thiosulfate coppers, we divide by 2 times by 2, and that means these two are actually a 1-to-1 with each other. So let's take a look at the questions. Make sure that you do all of these to 2 decimal places. And remember, the mean is the closest to. So your closest to is that one and that one, which gives you this. The percentage uncertainty will be, your calculation is your number of readings times by the actual uncertainty divided by the reading that you are taking. So because we've got a burette, there are 2 readings, a start and a finish one. That's the uncertainty, and this is the reading from titration 3, which you were asked to do. You put all that together and you get to 0.46. And the other thing to point out to yourself as you're reading through this is, as soon as you see 2 decimal places, remember to write it under here to remember when you get to that answer what you're supposed to be writing it to. On the next part of this question, you put an excess in because basically you want all of that copper 2 plus to react. You want it all to convert into CuI, and that means you get the maximum amount of iodine formed that is possible to form. So you need some sort of wording that explains that. Your indicator for these titrations is always starch. It goes blue to colourless, and it does that when all the iodine has reacted. So just get that down as a standard answer. And then when we take a look at the main calculation, of course you can see the other page at this point, but we need to start with the number of moles of thiosulfate because we know both the concentration and the volume of those to get the number of moles. We then work on the ratio part of it just here. So we're dividing by 2 times in by 2, so we've got 1-to-1. So that is also the number of moles of the copper in solution, and that's in 25. So we need to remember to scale it up to the number of moles in the whole 250. We're then going to use this to work out the MR of the substance. So we're going to go to MR is mass over moles. So the subtraction on the other side of the page would come to 5.60, and divide it by your number of moles gives you a MR of this. These are units, remember, of molar mass, the number of grams per mole. The H2o therefore is the whole mass take away the mass of the copper sulfate, which is 159.6, that gives you 55. And if you divide that by 18, you get to that, which rounds to 3 as a whole number. Remember, we have to do them as threes. And remember to write down the final formula down here at the bottom. So this question, then we've got a lot of information up here. The redox reaction takes place when copper metal, so give yourself some annotations. What you've got here is heated with concentrated sulfuric. A blue solution forms, that must be copper 2+, and a colourless gas is collected, measured at room temperature and pressure. The gas has a mass of this. So you've got a few possibilities for gas because that's all you're using. So this is all you could possibly make out of that in terms of gases. So you know your answer is going to be one of these. This is your copper one. Remember, copper's one of the odd ones out that does that at the end. So in terms of the calculation, we've got a gas volume. Therefore, we can work out how many moles of gas we've got. So that is the volume over 24,000, and it gives you that. So we also know that MR is mass over number of moles, so we can work through that with the MR. We need to convert it to milligrams. It was given to us in milligrams, and then divide it by the number of moles, and that will give us 64.1. And out of the possibilities, that matches with that formula there. So your gas is that. And then you need to construct your equation here. So we know we started with copper. We know we had that. We know we made that. We have copper 2+ in solution. So we'll go for some of the sulfate didn't actually change. And then we need to add the number of water, basically make it balance after that. So after that, you've still got some H2s around. They will never be H2 as a gas there in that because you've got aqueous things around and lots of oxygen around, so it will always make water. So putting all of that together then, we should end up with the coppers here, the waters here, sulfates, and we need some SO2 coming off of that. So we need 2 of those there so that we've got the SO4, and we need 2 waters to make that balance up as well. So there's your 2H2, your 2H2 there. You've got an extra sulfur here, sulfur there, and you should be able to find 4 extra oxygens above and beyond that. 1, 2, 3, 4.